So our last talk of the session will be given by Russel Arbore, who's a PhD student at Berkeley. And he'll be talking to us about optimization and equality saturation. Sorry, optimism and equality saturation.
I didn't catch it, so you're fine. All right. Okay. Hi, everyone. My name is Russel Arbore. I'm a PhD student at UC Berkeley. Today, I'm going to be talking about my work, Optimism and Equality Saturation. This was joint work with my two co-advisors, Max and Alvin. So over the last few years, equality saturation has really been kind of rediscovered as this super powerful program optimization technique with a wide variety of applications, including floating point programs, tensor algebra, computer-aided design, imperative program compilation, RTL design, quantum circuit design, a whole bunch of stuff. In fact, I will point out that these last two applications in particular have seen very recent work, as in at this conference, and you should go watch their talks as well. I'm sure they'll be great. We got one in the audience. So naturally, this success motivates thinking about using equality saturation for more complex applications. So for my research, I'm interested in thinking about using equality saturation for, say, production optimizing compilers. Mentally, you can think of this as a state-of-the-art C compiler. Can we build one of those using eGraphs? Today, there are several problems that kind of get in the way of being able to do this. So in this talk, I'm going to focus on one of these problems, which is how to perform optimistic analyses inside of eGraphs during equality saturation. So first of all, what is an optimistic analysis? So intuitively, at a high level, you can think of an optimistic analysis as being an analysis that infers a non-trivial loop invariant about some data in your program with loops. So in this running example program, we have a loop that we have some variable x that starts at 1. Let's say x is an unbounded integer to make things simple. And each iteration in the loop, we add some positive number to x. So the non-trivial loop invariant we want to derive is that x is always at least 1, right? And standard interval analysis techniques, already in the literature, will indeed discover this fact on this program as written. And performing optimistic analyses is important in a production compiler because many programs indeed have loops, right? So the issue is that when we try to analyze this program in an eGraph using E-class analysis, it turns out that you will not discover that x is always at least 1. This is because standard E-class analysis, which is the way you do program analysis inside of an eGraph, is pessimistic rather than optimistic. So intuitively, this means it will not discover that non-trivial loop invariant. So for this program, it would discover that x might be any integer, which is not particularly useful. Additionally, if we try to make E-class analysis optimistic using standard program analysis techniques, and you're not careful and you do this in a naive way, you might actually derive unsound analysis results. So later in this talk, we'll see that a naive optimistic E-class analysis will derive that x is always 1 in this program, which is clearly wrong. So in this talk, I'll describe why this phenomenon occurs and how we address it. So first, I'm going to dig a little bit more onto what exactly I mean by optimism. So for ease of both analysis and for equality saturation, we view all programs as data flow graphs. So this running example program that we have, we can transform it into the data flow graph on the right. This graph is in static single assignment, or SSA form. You don't need to know the details of SSA form to understand the rest of this talk. I will just point out that the phi node in this graph, the one with the C label on it, corresponds to that variable x in the original program. And in particular, it corresponds to the cycle in data flow dependency that the original loop necessitates. We have to represent it using a cycle. So in order to perform an analysis on this graph, we can convert the graph into a series of analysis equations. Each analysis equation defines one variable. This variable is the abstraction for a node in the graph, and it's defined as a function applied to the abstractions of the inputs to that node. So these specific equations correspond to an interval analysis on the original graph. Now, these equations are mutually recursive, so we can't just pick some arbitrary order to solve them one by one. Instead, what we do is fairly standard, is we pick some initial assignment to the variables, and then we iterate the analysis equations until either a fixed point or a post-fixed point has been reached intuitively until the variables stop changing. Now, this initial assignment to the variables, so what is the initial assignment, matters a lot in terms of precision. So in particular, we can either initialize all the variables to be the largest possible interval, so negative infinity to infinity, or we can initialize them all with the empty interval, which we write bottom. We write as bottom. And depending on which of these initial assignments you use, you will get a different final analysis result. Now, these analysis results may differ in precision, but a core tenet of abstract interpretation is that both of these are sound. So if you look at, and you will see that both of these results are indeed sound, even if they differ in precision. Okay, next I'm going to describe some basics of equality saturation. So equality saturation is this program transformation technique where we can perform rewrites on a program without destroying the old program. So in particular, you store your program in a data structure called an egraph, which remembers all the ways that I can express a particular value in my program. So the typical workflow is after you take a data flow graph and initialize an egraph with it, I will run a bunch of rewrite rules that discover new ways of writing values in the program. And then after I've done this to my liking, I will extract a final program from it according to some cost function. Now, let's take a kind of simple example. If I have a program that consists of the two expressions on the left, I can convert this into a data flow graph on the right. All data flow graphs are egraphs that are just trivial because no equalities have been discovered yet, or no interesting equalities have been discovered yet. We can apply a rewrite, which encodes the commutivity of addition, to discover that the two addition nodes in the egraph are equal. We mark this in two ways. So one, we draw a red dashed edge between the two nodes. And then two is we change their labels to be the same. So in this case, now the two plus nodes are both labeled with C, which says that they're in the E class C. And they're in the same E class because they're equivalent. And then additionally, egraphs can efficiently propagate congruence of functions. So the equality between the additions implies one new equality in the egraph that we can discover. Now, during equality saturation, we may also want to analyze the nodes in the egraph, or the E-classes in the egraph, I should say. This is because some rewrites may be conditioned on an analysis result. So being able to analyze E-classes precisely may allow us to do more precise rewriting. Now, just as with normal data flow graphs, we can view E-class analysis as a set of equations. The difference is that these equations, each variable corresponds to the abstraction of a single E-class rather than a node. This is because any abstraction for an E-class is going to be sound for all the nodes in that E-class because all the nodes are equivalent. That's why they're in the same E-class. Now, when I want to analyze two nodes in the same E-class, I can do that, and each node is going to have some transfer function that gives you the abstraction for that node in terms of the inputs to that node. When I want to get the abstraction for the E-class, I combine those analysis results. This means that as I perform more rewrites in egraph, my E-classes get larger. This means that my analysis of each E-class is going to get more precise, which may in turn allow me to do more rewriting, which in turn allows me to do more analysis, and this goes back and forth. Okay, let's finally return to the original problem. Okay, so consider this egraph on the left. It's a very simple egraph. It just represents the term 1 times 5, where I've applied the rewrite 1 times x is equal to x, because multiplying a number by 1 doesn't change it. So in particular, I put the times node and the 5 node in the same E-class. Okay, I can convert this into a set of interval analysis equations as shown on the right. And if I try to analyze these set of equations, and in particular, if I try to do the optimistic analysis of this set of equations, I will actually arrive at an unsound analysis result. So in particular, my analysis will say that the E-class B can't be any value. It's in the empty interval, which is clearly false because the original program, 1 times 5, is equal to 5. So something's wrong. Now, also notice that we can instead initialize all the variables with the largest possible interval, and that gives us the pessimistic analysis. And unlike the optimistic analysis, this one is sound, and in this case, it's also precise. And in fact, this is what existing E-class analysis systems do. They always compute a pessimistic analysis. So at least for this example, they will indeed compute an analysis that is sound. And in this case, it's also precise, so what's the big deal? Okay, let's return to our running example program. So we convert this into a data flow graph. We can apply the same rewrite, because 1 times 5 is part of this program of 2. And then we can convert this into a series of interval equations. And we can do the same procedure. So we can perform optimistic analysis on this. And indeed, intuitively, because of that 1 times 5, we will still arrive at a unsound analysis result. Notice that this E-class C is analyzed as just being the interval 1, 1. This is what I meant earlier by saying that we will arrive at the result that x is always 1. We can instead perform a pessimistic analysis on this set of equations, but now we do not have a precise analysis result. So notably, this E-class C, which represents x inside the loop, it's in the interval -infinity to infinity rather than 1 to infinity, which is what we want. Now, it turns out that there is a solution to these equations that is what we want, which is that we find that x is always at least 1, but it's not obvious how to compute this solution to the equation. So in particular, what would I initialize all my variables to in order to arrive at this particular analysis result at the end? It's not at all obvious. So before we get into how we address this, I want to point out that there are 2 kinds of cycles in E-graphs, and this will be relevant. They are unfortunately not very well highlighted on the screen, so I will refer to them as the left cycle, which is the one between the phi node and the plus node, and the right cycle, which is between the times node and the E-class B. So that left cycle corresponds to the loop in the original program and corresponds to an actual data flow dependency cycle, while that right cycle corresponds to, or rather it was created by this rewrite, 1 times x gets rewritten into x, and does not correspond to a loop in the original program. What it instead corresponds to is that 5 in the E-class B is equal to 1 times 5, and 1 times 1 times 5, and so on. In other words, I can multiply 5 by 1 any number of times, and I'll still have 5. Unfortunately, this also corresponds to the program 1 times 1 times 1 times 1 times 1, and so on, or x equals 1 times x, which either way you say it is not particularly well defined, but we still analyze it. For more details on what I mean by represent, I encourage you to take a look at the paper. Also, I'd like to point out that this original observation that E-graphs have these 2 kinds of cycles, I should credit Sam Coward, Cheung Zheng, and Alexandra Silva. They first noticed this, and this work builds off of that observation. So as we saw before, optimistically analyzing the right cycle is problematic. It produces unsoundness. But we want to optimistically analyze the left cycle for precision reasons. So the crux of the optimistic E-class analysis algorithm that we will describe is to treat these kinds of cycles differently. So just to give another name to these kinds of cycles, the one on the left that corresponds to the loop in the original program, I will call well-formed. And the cycle on the right, which was created by this rewrite and does not correspond to a loop in the original program, ill-formed. Okay. Now, I will actually describe the algorithm. So first, what we're going to do is we're going to notice that the well-formed cycles in this graph are exactly the data flow cycles that are encoded by loops in the original programming. That's how we defined well-formedness versus ill-formedness for these cycles. So we are going to identify these cycles with constituent what are called back edges. These are edges going into phi nodes that correspond to iterating a loop in the original program. So in this diagram, the blue edge is the back edge and corresponds to defining a new value of x in terms of the previous value of x in the previous iteration of the loop. Next, we're going to compute a pessimistic analysis on this E-graph while ignoring this back edge. Intuitively, this is conducting analysis that is going to be sound, assuming that loops never execute once. So notably, this is not all program executions. This is only program executions where loops iterate at most once. Now, I will point out that because this is a pessimistic analysis, it is indeed sound. So in particular, the ill-formed cycle does not poison the analysis result. So the analysis result will be sound for this subset of executions, but it is sound for that subset of executions. Next, we can, so I should also point out that this is where the optimism in the algorithm gets inserted. So although at each step of this algorithm we're computing a pessimistic analysis, The optimistic assumption is this original version of the analysis where we're assuming loops execute at most once. Okay. Next, we're going to compute an analysis result that's sound, assuming loops execute at most twice. And the way you do this is you do exactly the same thing. You perform a pessimistic analysis of the E-graph. But along back edges, you can use the result from the previous iteration. So we can use results from the pessimistic analysis, assuming loops execute at most once. And then we can repeat this k times to get an analysis that is sound, assuming that loops execute at most k times. OK, then this outer process we repeat until a postfix point has been reached. So intuitively, we repeat this until the analysis variables for all of our E classes stop changing. At this point, the analysis is sound for any number of loop iterations, so for any program execution. And at this point, finally, we have a result that is sound totally for any execution. OK, so I encourage you all to take a look at the paper for more details on how to interpret cycles in E-graphs, more details on the proposed algorithm and its proof of soundness, more details on how to integrate optimistic E-class analysis into equality saturation, and empirical performance results. And with that, I'd like to thank you all for listening, and I'd be happy to take any questions.
Thanks, Russell. We have plenty of time for questions.
Would a recursion bring some problem of computing the fixed point?
Sorry, can you say that louder?
Would a recursion bring some problems in your computation?
So the way we formalize this for this paper is we just deal with control flow graphs in a single function.
A single while loop, right? But if it's like different levels and all that.
So you could have nested while loops. That we handle that fine. But the formalization is for a control flow graph in a single function.
So what about probabilistic program? Do you think do you foresee that it's possible to generalize it? It seems to correspond to some complicated.
I am nowhere near an expert enough in probabilistic programming to answer that.
Hi, Tom Ball, University of Washington. So those two loops, I mean, the second one on the right-hand side's really just an equivalence class, right? It's not really a loop in any sense that I look at it. It doesn't, so I mean, duh, you should treat them differently. I mean, I don't really understand why you would call that thing on the right a loop. I mean, this is just maybe nitpicking, but that's an equivalence class, so
I mean, in some sense, I agree. And the point of this work is kind of to bridge the gap between the mechanics of the E-graph and what we intuitively know to be true. I agree, intuitively, that is not a loop. That doesn't correspond to a loop in the original program.
But it was treated as such somehow in your transformation into data flow analysis.
So in particular, so I should also emphasize, the way we formalized E-class analysis, this is standard. We did not do anything weird there.
Right.
Prior work formalizes E-class analysis equations in the same way. So the first contribution of this work is to point out that this weirdness happens, and how should I phrase this? It's a facet of the prior work and how E-class analysis is formalized.
I see. Okay, thank you very much. Yeah, cool stuff. Thanks.
Hi, Xiang from Columbia. So yeah, E-graph is great, and so I wonder how much benefit can you get when applying such an optimism E-graph analysis when in real world E-graph compilers or optimizers,
Yeah, so this is something we did not evaluate to the extent that I would like in this paper. This is something I'm interested in continuing to evaluate. So in this paper, we just mostly focus on the theoretical aspect. That being said, I think it's kind of hard to evaluate this right now. And it's sort of a chicken and egg problem because there's not really a E-graph-based compiler that handles a complicated language with loops or recursion or that kind of thing yet. I think because we don't have the capabilities to properly handle them yet. So I think we will be able to answer that question once we have the capabilities to then build the thing to then empirically evaluate how much it helps.
Okay, thank you.
I have a question. So for example, as it was on the screen, so there was example, for example, b equal to 1, then we assign b different values. So as I understand, we solved this problem in E-graph, and I have a question. So there is still kind of trace of modifications that happen to b before we separate them, kind of. Do we just lose track of all those traces, or we still can optimize them?
Sorry, I'm not sure I understood the question.
Yeah, so for example, B is mutated multiple times during evaluation. So with this new approach, on the traces of these mutations, they're getting lost, or they still, for example, can be somehow optimized?
So one aspect of SSA form that I didn't go into the talk is that, let's see, way back. How far back? Let's see. Yeah, so the program on the left has mutable variables. So there's this mutable variable x that gets mutated multiple times in the loop. When we convert it into this data flow graph, and when we do a process called SSA translation, this graph on the right, you can define semantics for it without having mutable variables. And this is the standard way of dealing with programs in eGraphs. You usually don't talk about variables that mutate. You instead talk about definitions of values that are immutable.
Okay, got it. Thank you.
Hi, this is Byron Zhang from University of Chicago. So at each step of your iteration, when you remove the back edges, in the graph, do I get a DAG? Do I get an acyclic graph then where I can just do a topological traversal? And
Not quite. So if you ignore this blue edge, right?
yeah.
There is still a cycle. It's the bad one. So
I
that
see.
means, and this is why, by the way, so if you look at E-class analysis implementations, it's not a single pass over the whole E-graph. This is why. Because there are still cycles. They're not usually that helpful, but they still exist, and you have to deal with them.
I see, but for these cycles, because we know that they're in the same E-class, wouldn't it necessarily mean that the value will be the same?
So you can make more complicated examples where the cycle spans multiple E-classes.
Right, okay. Okay, thanks.
Just to actually make this concrete, imagine I have a program, x equals something, y equals x plus 2, and then z equals y minus 2.
I see.
You will get two E-classes, and there's a cycle between the two.
I see, but it's not, they're not all equal to each other, but you have a middle and
Exactly.
intermediate value in the middle. Thank you.
Hi, good talk. Will from UIUC. I did not understand what does this algorithm or this whole analysis have to do with E-graphs in specific. The whole thing can be applied to general abstract interpretation to general program analysis also.
I agree. I think the reason, like the motivation for it is specifically eGraphs, right? Because of this, the ill-formed cycles that happen due to rewrites in the eGraph. And they are an artifact of performing these non-destructive rewrites in the eGraph. So in particular, there are some variants of eGraph systems where a rewrite such as 1 times x goes to x would not keep 1 times x around. Intuitively, because like who cares about 1 times x, right? But there are, that doesn't cover every case, but in such systems, you would not get this cycle. You would just get 5 instead of the times node for the E-class B. So I would say you could apply this algorithm to any data flow graph. It's just that maybe the motivation for it is specifically the E-graph.
Thank you.
Thanks, Alvin. Let's take the remaining questions offline. It's time now. Let's thank all of the speakers once again.